So today, this talk is about me trying to tell you what I am doing in my PhD. I'm not a lifesaver. I was just asked if I try to save lives from my PhD. I'm not. So let's see. I called it a strong along a Mobius band, and I hope it will become clear what I mean by that. I'll talk to you about surfaces and configuration spaces. So let's go. Maybe. Oh, no, yes, and I have to press, where do I point? Yes? Right. So I want you to, it was Halloween last week, so let's imagine this spooky scenario. You are you wake up and you're in this very long dark corridor, okay? You keep walking in it and you're like, okay, I'm trapped. There's no way out. It's always the same. But then, right, that's you down there with your lamp. You're trying to find out a way out. Then you become a bit cautious. Imagine that the corridor is starting to curve a bit and you're like, aha, I think I figured this out. This is a circular corridor. So maybe let me find how long it takes for me to walk around and come back. So you're clever. What are you going to do? How are you going to figure this out? Well, you drop your hat down the floor and you're going to start walking until you find your hat again. 2 hours later, if you pardon my animation skills, you find again your hat. So you're like, aha, now I know what's happening. The corridor is circular, and it takes 2 hours to walk around. So that's you and your lamp going around this corridor. And what is this shape? This shape is called an annulus, or also known as a flattened cylinder, and it takes 2 hours to walk around it. Okay, we can rest assured that we have understood what's happening, but I have a plot twist for you. There's something you didn't notice. What you didn't notice was that 1 hour through your walk, on the ceiling of this corridor, there was your hat. When you actually notice this again, the second time around that you go, you're confused, and you're like, this cannot possibly be happening. And when you realize what has happened, well, there's a way to figure this out. Your corridor is not actually circular. What happened is that somebody took your corridor, and instead of gluing it around circularly, they gave a twist upside down. So as you were walking, you ended up walking on the ceiling again when you were going on the other side. And then you had to walk twice around to come back to the same side, to the same point, and be on the same, not on the ceiling. So what concept are we figuring out now? We're figuring out the concept of a Mobius band, which is essentially a strip of paper that you glue around with a twist. And well, the point is that if you walk around it and you come back, you sort of come upside down and you have to walk twice around it in order to come back in the same direction. So for example, here we see a little crab walking around, and you'll notice that the direction of its claw changes every time it walks around. It has to go twice around to come back and be in the same direction. So what's happening here? Let's completely forget about what I've told you up to this point, and let's go and study a bit of topology. So what's topology? Topology is the branch of maths that I am studying. It's the study of shape up to deformation. And what do I mean by shape? There are lots of different concepts lots of places in the world where shape appears. For example, what I mean up to deformation is that, well, there's this joke that a topologist cannot tell his mug and his donut apart, because if you made them from plastiline, you could push one gradually to the other, and they sort of look the same for a topologist. It's the same shape. But where does shape appear in general? Well, in cosmology, theoretical physics, when you ask a question like, what's the shape of the universe? You're asking a question about shape. We have to understand this somehow. But also more recently, like networks, neural networks, like you have to understand like how connected they are, etc. That's also a question of shape. And topology can go and attack all these and try to give answers. So one particular kind of shape is a surface, which is a two-dimensional shape, essentially, that whenever you stand in it, you only have two sort of independent directions to move. Like, you couldn't tell if you're standing on this floor or, you know, if you're on something like that Mobius band, if you just had only a small area around you to look at. So these are some examples of surfaces. There are these three sort of examples downstairs that for geometers would be three different geometries, but for me, because you can sort of push one to the other, they look the same for me, essentially, even though the distances are different. This is quite a bit like the sort of surface I like to think about. Surfaces can appear as graphs of terrains or of data in data analysis. So I have a screen of Pac-Man up there, and you might wonder why. Because Pac-Man also lives in a two-dimensional space. Like, it has two directions that it can move. And recall that there's an exit on this side that comes back from the other side. So essentially, really, Pac-Man is not living on a plane, but is living on a cylinder. Because really, the two sides are glued. Okay, so, right. So to get to what I am studying, let's have a small detour on the concept of symmetries. And there is this motto in maths that if you are studying an object, to study an object is to study its symmetries. You want to understand like how you can change an object and still it looks the same. So what do I mean by that? For example, symmetries of a square, you can take a square and rotate it in all possible ways or reflect it. And these are symmetries of the square that keep the shape the same. Another sort of symmetry is a set, a word. Consider a word like, for example, I took the word sit. And then you take all possible permutations, or nonsensical anagrams, if you want. Some of them mean something, some of them mean nothing. But if you blur the letters and you don't worry about, the fact that what letter that is, it's just a three-letter word. That's a symmetry of it. And how many of them there are? Well, okay, 6, 3 times 2 times 1. You might ask yourself why. Well, don't want to speak now more about this, but this is something from combinatorics. I have also drawn here an example of how studying these permutations, these symmetries of a bigger word can very quickly lead to very big numbers. And the answer is, always going to be given by a number like this, a multiplication like this. So it grows quickly. But, okay, so that's how you study symmetries of a simpler object. But how about a surface? How about a shape of the sort that I am thinking? Well, for a word, we put labels. Here, let's draw curves to keep track of what's happening. You can take this square, and a symmetry of it would be literally, imagine it made out of rubber. You put your hands on it, and then you move around. It keeps it being a square. Suppose that its sides are fixed somewhere. And then, well, but the things inside it have moved. And this visualization helps us see how it has moved. And understanding this actually is something important. For us to understand this surface means to also understand how it can change in all possible ways. Right, I have here a torus, which is the surface of a donut. This is a surface that I care about. And I'm about to give you a symmetry of the torus, which is, observe the following animation. Nope, want to go back here. So in this animation, you see the torus being torn apart at a point, then rotated, and then put together back in the same way. And then you sort of undo a bit so that it looks simpler. So this is called a dent twist on a torus. And this is a symmetry that is not of the format we studied earlier. It's a bit more tricky. So, okay, the next few slides are breaking this down. So, okay, to study, we need to study all of these. And okay, a way to study this is by configuration spaces. And the way we do it, essentially, is we put some points on the surface. and then consider all ways of choosing these points. Now, all ways of choosing these points, there's infinitely many ways, but we can put them together into another shape called the configuration space and apply topology methods to it. Okay, but then soon we end up having problems, like we have to consider situations like particles moving on the surface, like before when we moved into the Mobius band. We have to consider situations like this. Okay, now given all this, what I really do is that I consider how these two concepts, symmetries and configuration spaces, interact. And I guess that's what I want to tell you. And I mean, okay, I have to skip a few slides, but because I miscalculated time. And well, the conclusion is, what do I get out of that? Well, it's complicated, but I have some results. Well, thank you very much for your attention. Thank you.
Thank you so much. I must say that I'm very happy that I'm not a topologist, because otherwise I would bite my mug, not my donut. So, does anyone have any questions for Andreas? Oh, I start here because it's closer.
Thanks. Do you know anything about how the topology of the roof on the great courtyard of the British Museum was translated into actually building it, the application into the actual manufacture of the roof?
No, I have no idea. No. But I can look it up, and then maybe we can discuss it. Yeah.
No worries, you will have a break for it later.
Thank you for the talk. It was really interesting. So has your work, is pure mathematics, has it got any sort of applications, like in sort of more of a physical way? Does it solve any sort of problems?
Well, that's an interesting question. So mathematics, and I think there are a couple of mathematicians in this room, well, sort of sometimes do it for its own sake, and then you find that, oh, incidentally, it has an application. I have found out that studying these symmetries that I told you is important because sometimes, in theoretical physics, string theory is an example. You have a string, and it moves through space and time. What it traces is a surface, and in order to study that, you have to quotient out, essentially, by all these symmetries. And I found people studying theoretical physics having the object exactly that I'm studying appearing there. Configuration spaces are also like a phase space. It's like all possible ways that a physical system could take, and like a point on that phase space is like a configuration somehow. These things appear, but I study them for sort of their motivations from pure maths that lead to that, yes.
Thank you so much. The time is up, so thank you again for the presentation.